Hi, welcome back to the AP Calculus Derivatives lesson section. In this video, we'll be going over related rates, or the introduction to related rates. And to begin with, this is going to use a lot of what we learned in lesson 8, which was derivatives, implicit derivatives, ones that don't just go with respect to x, but can work with any variable. So, to get started, let's look at what a related rates question really is. If we're talking about related rates, we're talking about how one variable would affect another variable and finding the relationship between them. So for example, if I were to, let's see, I'm going to draw a little cylinder here. Actually, let me do this. I'm going to copy it directly. If I were to make a cylinder here, and I'm just going to do a little editing here to make it look more real. Let's see. Okay, good. Here's our cylinder. So now if we have some variables we can look at here. We have a height, and a radius, and those are the only two variables that don't change in this specific cylinder, in this solid cylinder. But when we move into calculus, we have to start looking at other variables, like when things are changing. And calculus is all about looking at the relationships between things changing and their environment. So for example, if we say that there's a certain amount of water here at this height, and there is a little faucet coming out of the side here. Okay, not bad. If we have a little faucet draining water out of here, then you might be able to say that it's draining out at a constant rate. Most faucets, if it's coming directly out of the bottom, you can pretty safely assume that it's going to be dropping out at a constant rate. So if you think about it, one variable that we can take from the radius and the height is the volume. So if we have a volume that's changing over time, then we take our v, and if we take the derivative with respect to time of our volume, then it's just going to look like this. And so if these symbols are getting ahead of you, just think about what they mean. Part of why I like this notation, and part of why it's used so much, is because this really means the d is a small change in volume per small change in time. So it's kind of the instantaneous change in volume per amount of time. Now, what that means is, if this is draining out here at a certain rate, then the volume is changing at a certain rate, at a constant change. So we could say this is negative 100 centimeters cubed. And so this is one value. Now, what we can do with this is say we have a v. If we get some other information, we can solve a related rates question. So now that we've gone over some basics, let's kind of set up a real problem here. So let's say that the radius is 5 in this cylinder, 5 centimeters. Gotta have a unit on there. The radius is 5 centimeters, and our height our volume is originally 1,000 cubic centimeters. Now, if they give us these two pieces of information and also said that it was draining at 100 centimeters cubed, meaning that it's got this negative change, it's decreasing negative 100 centimeters cubed per second if t is our seconds unit. Although this seems a little big, it seems a little unrealistic, draining 100 centimeters cubed per second, so let's call t's in minutes. Now, whenever you're doing a question like this, they'll always tell you what t is. And it doesn't really matter, but I'm just trying to keep this a little realistic here. So, we have the change in time, how much it's decreasing in pure volume, the original volume, and the radius. And so, let's look at something that we already know. We know that if we're talking about related rates, we're talking about relationships, meaning we can look at the relationship between volume and these other variables, which happens to be v equals pi r squared h. And so now that we have this, we can solve for something. Now, in this example, the question is going to be, what is, here, I'll just type this out, give it a little bit smaller here. What is the change in height per minute? So your book might just go out ahead and tell you find dh dt, but if you see something like this, you just have to look at exactly what it's saying. The change in height per minute is going to be h over t, or dh over dt. Now, if we plug in our numbers here, 1,000 equals pi times 25, 5 squared is 25, times h. We see that we can solve for h just by, if we divide 1,000 by 25, we get 40. Divide the pi over, we have 40 over pi equals h. So this is our height starting point. And so although we can solve for this, this isn't really what we need. What we need is to find dh dt. And so to do this, we look and we see we have dv dt, but we don't have dr dt. In fact, there's no such thing. Dr dt is 0, because dr dt means change in radius over time, and there's no radius changing here because this is a cylinder. As the water level decreases, the radius always stays the same. So dr dt equals 0. But we don't even need to look at this. What we do know though is if we take this, here, let me make a copy here. If we take this and take the derivative, then we can find the relationship between dv dt, which we know, and dh dt and solve for our answer. So let's go ahead and take the derivative of both sides. So it's going to look like this. Actually, before we do this, let's take this r squared out and replace it. Because the r squared never changes, it's always equal to 25. It's always equal to 25 centimeters. We can go ahead and put this in instead. I'll make a copy. So now this is a lot easier to deal with. we have v equals 25 pi h. And so now take a look at this. This is our constant, so we can leave this out when we're taking the derivative. So if we take d dt of both sides, we get dv dt equals 25 pi, that stays by itself, times dh dt. It's direct derivative. We just have the single variable here. It just goes straight to dh dt and dv dt. And so now that we know this, let's go ahead and take the information that we have and plug it in. Now we know this is true. This is given to us. dv dt is negative 100 centimeters cubed. So let's take that. Let's clean this up a little bit. We have negative 100 centimeters cubed equals I didn't do that. Okay. 25 pi times dh dt. So now I'm going to move down a little bit here. Scroll down so we get more room. Now if we take this and solve for it, I'll just move it down. If we solve here, we see negative 100 divided by 25 pi equals dh dt. And so our answer is right there. We're done. So to rewrite this, this is negative 4 over pi. And so this is our dh dt. And if we think about it, our height is in centimeters. This is the unit we put on there. And this value makes sense because it's supposed to be negative. We want it to be negative because if we're decreasing here, this height is going to be, change in height is going to be negative. This height of the liquid will always be decreasing. And so I hope this introduction made sense. If you didn't completely follow what was going on, I hope you at least get the gist of the basic idea of how related rates works, because if you kind of develop an intuition for this, you can see what values you need to solve for. And so that's why I'm leaving this lesson 9a, and so next lesson 9b will be going over another related rates example. And so we'll do one, I'm pretty sure we'll do one with a cone, so that we've got a change in radius as the water's flowing out of it. But I think that we can handle a little bit harder example. And so I'll see you in the next video. Thanks for watching, and goodbye.